So hello, everyone. I hope you can hear me. My name is Monica Villanueva. Today I'm going to be talking about Avalon on behalf of all my collaborators. You may notice that there's been a slight change on the title. So now it's called Can We Improve the Validation of Match-3 Games Level Generation? So as you can see, this is a multi-team, multidisciplinary effort. So I just want to give my collaborators a shout out for their contributions to the project. And Joachim, Alessandro, and Linus, apart from myself, we are part of the SEED team. It's an applied research team inside of Electronic Arts. A little bit more about me. I've been working at SEED for more than 6 years now in different areas. So I've done work in audio and animation, and I've written and published papers apart from shipping content into game. So one of the projects that we have actually shipped is this machine learning model that generates facial animation, lip sync animation, directly from recorded speech. And this system has actually helped drive the animations that you will see in the follow FC cinematic.
On est là pour parler tactique aujourd'hui. Cela peut paraître ennuyeux, mais au contraire. La tactique, ce n'est pas seulement des datas et des réunions sans fin. Il faut voir le football sous un autre angle. Dans le haut niveau, le foot se joue aussi dans la tête. L'intelligence de jeu est aussi importante que la technique. La tactique au haut niveau, c'est ce qui fait la différence. C'est ça qui rend beau le football. Le football, c'est aussi la tactique. Elle s'applique sur deux phases de jeu. Quand tu as le ballon et quand tu ne l'as pas. C'est simple, individuellement et collectivement. Comment tu attaques et comment tu défends. Par exemple, sur le deuxième ballon. C'est resté simple. Celui qui a les cartes en main, c'est le joueur. Toujours. L'important, c'est que le message soit clair sur ce que tu veux et tes intentions pour tes joueurs. Vas-y, sois curieux, ouvert, observe, étudie, tente. Il y a 1000 possibilités, 1000 formules. Il ne faut pas être conventionnel. Joue ton jeu. Crée. Welcome to the club.
So today I will talk about level generators and how they can be applied to Match-3 games. I will introduce the motivation for our research. I will explain the Avalon method and show a little demo on Unity. Then I will touch briefly on the evaluation framework and show more results. I will finish the presentation by talking about challenges and opportunities of level generators in production. So let's start with level generators. Most of you will be familiar with procedural level generators because they are widespread in the industry. They are based on rules. This makes them easy to be understood, but also hard to define. And also, if the logic of the game changes, then these generators need to be rewritten. And of course, they need validation, especially in cases where the rules don't cover the behavior. On the other hand, we have machine learning methods. These are newer. There's academic work in the area, but there's not so many of them actually in production in games. They learn from data, which on the other hand makes them harder to be understood. But the good side is that there doesn't need higher or big expertise in the area. And if the game logic changes, their generation can be automated. Of course, they also need validation. So today I'm here to talk a little bit about how research can help game production. And the question that I posed in the title for this talk is if we can improve the validity of level generators. So we think that we can do that by using machine learning methods expanded with auxiliary information. And in particular, I'm talking about gameplay information related to the difficulty of the level. So I have here a couple of examples of different game genres just to get you inspired. So you can imagine, for example, in a racing game, the difficulty might be related to the number of turns in the track and the time you're allowing the player to race or finish the lap. And these tracks may have different styles. For example, we have here, these like rounded tracks that might be suitable for, I don't know, F1 kind of game, or these open-ended tracks that are more suitable for rally games. We also have here like a conquest mode in a shooter game where the teams are unbalanced. One of the teams uses short-range weapons versus long range on the other side. And by asking the generator to create levels with different average hit distance, we can keep the game balanced, or we can bias it towards one of the teams. Okay, so for the rest of the presentation, I will focus on Match-3 games. This is because we prove our idea by collaborating with Track 20 on a Match-3 game called Plants vs. Zombies Match. And with this, I don't want to take away credit from procedural generators. They still have value. So we actually implemented one of these initially in order to generate more data for our machine learning model. And one of the level designers that was working with the tool said that this is wonderful for breaking the creator's block. And if you want more quantitative metrics, this procedural generator plus validation bots, it sped up the creation process up to 3 times. So Match-3 games, just a brief recap for people that might not be very versed in the area. So it's a kind of casual puzzle games where the player moves the tiles around in order to match 3 or more of the same color, make them disappear from the board. Different games have different rules. So for example, we have Bejeweled. I think we can click here. Their main mode is just to accumulate points, but they have other modes where you have like a specific goal to achieve. This is also very common in Candy Crush kind of levels. And another common feature is that, you know, if players match more than 3 tiles, they can create power-ups. We also have Lily's Garden, which is a little bit special in that tiles are not swapped. But the player just click on them if they are already together. So level generators for Match-3 games seem like a really good idea because they have a high demand to push out new levels during the live service. And it's also a great opportunity to offer personalized content. Unfortunately, there's not a lot of academic work that deals with level creation in these kind of games. Today, I'm gonna explain or talk a little bit about 2 of them. Bolz et al. That works with Candy Crush levels, and Halt et al. That works with Lily's Garden. So let's start with Bolz et al. So their main goal is to generate levels for Candy Crush where they display suitable patterns. In particular, they focus about symmetry of those levels, and they use generative adversarial networks and Markov random field in different flavors to achieve this goal. So some of the limitations of this method is that these models are not controllable. So a level designer cannot select the type of symmetry that they want to generate and the generators just follow the distribution of the original data. And also, once the levels are created, they are not evaluated in terms of playability, so we don't know if they can be solved or not. On the other hand, we have Hall et al., which goal is to control the generation, and they compare an unconditional and a conditional GAN. They use two conditions, map shape and piece distribution. Unfortunately, in this case, the limitation is that they only use these two conditioners, and one of them doesn't really work very well. And in terms of playability, they evaluate if the level can be started at all. That's what they mean with color island. So if there's at least one at the beginning of the level so that the player can start, or if the generator places tiles outside of the map shape. That's what they mean with broken pieces. So we wanted to address some of these limitations with Avalon, which is an approach that we published at the Transactions on Games journal this year. So in general, our motivations are threefold. We want the generators to be controllable so that the designers can choose the features they want to see in the generated level. At the same time, we want those levels to be solvable. And the third goal is that we want to learn from levels that have been created by our designers. I'm saying this because there are some other approaches that use, for example, reinforcement learning from scratch. So they create levels, but there's no way to influence them with pre-created or human-created levels. And in terms of our user or our use case with Match-3 games, I would like to mention these assumptions that we're taking. So we're focusing on the layout of the level and not necessarily the whole level. We consider valid levels, those that can be solved within 20 moves. And this was a requirement by the game designers because they want to have a consistent playing experience. And as a proof of concept, we fixed the goals to be 60 red matches. So I'm going to explain on a high level how the method works. So we start with our level designers. They have created some levels, and we accumulate them in a data set. Those levels are converted into a format that can be understood by machine learning. And we extract features that we deem important. Those features can be extracted with bots or by humans. If the game is online, we can have player data. If it's not, we can use, for example, tester data. And for our use case, we focus mainly on the median number of moves. That's the proxy for difficulty that we are using for our method. Additionally, we also extract information about the symmetry and the size of the board. And then we take that information paired together with the level it was extracted from, and we save it back into our data set. During training, we feed the level condition on the data or the features that we extracted, and we train a generator. In our case, we're using a conditional variational autoencoder. So during inference, the level designers will be able to control the generation based on the features that we extracted before. Again, the median number of moves that the level have to be solved with, the symmetry, and the size of the board. This information is fed into the generator that hopefully will create levels that follow those conditions. And this output can be converted back into a format that can be consumed, again, by the level designers in case there is need for further editing. So let me just show a demo in Unity where I will show all of this, and I will also prove that the levels are playable. So here we can select the Avalon model, and we are using it as a batch processing tool. In this case, we can select a range of different sizes and multiple symmetries, and the model will just sample among the possibilities. Inference takes 2.5 milliseconds per level, plus some post-processing and data conversions that happen in engine. But as you can see, the whole process is really fast. This is like real time. I didn't speed up the video here so far. And I will be playing the level myself. Here I did speed up the video in the interest of time, but you will see that I'm able to finish the level before I run out of moves. Yeah, and I did it. So briefly on the evaluation. So we want to validate that adding this number of moves conditioner actually helps. So I compare here the Avalon version against itself without this conditioner. And we call this the vanilla version. So the downside of this version is that we need to evaluate the levels after we create them in order to see if they can be played or not. And this requires extensive testing, either with multiple game testers or using bots until convergence. And it might take up to 15 minutes per level. On the other hand, with the Avalon generator, so we are allowing the level designers to choose the number of moves they want the level to be solved. So that reduces the need for validating after creation. And also it's a flexible framework because we can extract those statistics from different sources, as I mentioned before, either automated, bots, or human data. And in terms of metrics, we try to design them according to the goals that we had at the beginning of the project. So we want controllability, so we measure how accurately the levels follow the conditioners. Oops, sorry. In terms of playability, we compute the number of valid levels that we generate. And the third goal was to follow the style of human designers. So we have to evaluate the style of the generated levels. So at the beginning of the presentation, I mentioned, or it's in the title really, if we can improve the validity of level generation. And the results show that we can indeed. So the Avalon generator not only generates more valid levels than the vanilla version, but it also generates more valid levels than there were originally in the training dataset. So how well do we follow the conditioning? In general, our quantitative metrics show that we follow it quite well. But by adding this number of moves conditioner, we might be hurting some of the other metrics. So for example, we can see here that the size of the board, the accuracy of that is slightly lower for the Avalon generator than the vanilla version. However, we achieve 100% accuracy in the symmetry because we use a partial generation approach. And this solves one of the problems that was studied by Boltz et al. That I mentioned at the beginning of the presentation. Now, the number of moves is only followed accurately 1 out of 3 times, but this is more control than having no control at all. Unfortunately, the metric that we designed to evaluate the styles doesn't really correlate with human perception, but this seems to be another area where the accuracy might be affected. So now, in order to validate or understand better the results, I'm going to show 2 more demos. In the first one, I will create a level, an easy level. I want it to be solved in around 10 moves. In this case, I'm going to use the validation bots instead of playing myself. So we start with 20 moves. I'm increasing here also the speed of the simulation. And we can see that the level can be solved with enough moves to spare. In this second demo, I will create a hard level. And I'm saying, for the sake of it, to be solved in 39 moves. That's a lot. So we will start with 20 moves. You will see that the bot uses all of those, and then it gets 20 more, and then it's able to solve the level. But we also have a tool for visualizing these results. So we are running the bots 30 times until convergence. And we can see that for the easy level, all of the runs finish in less than 20 moves. While for the hard level, some of them, or some of the times, it can be solved under 20 moves, but most of the time, it needs more moves than that. Actually, we can see here the actual median. So here. The easy level can be solved in a median number of 9 moves, and the hard one, 27. And we can also see here that that means it needs between 5 and 6 trials in order to solve the level. And as I mentioned before, I will finish the presentation by talking a little bit about challenges and opportunities of level generation in production. So our results show that unfortunately we need more data, and this can be challenging when the game is not live, so you don't have a lot of levels, or just the game doesn't have a lot of levels in general. You can use like the procedural generators in order to add synthetic data to the data set, but that might come into issues when you have a style that you want to achieve, right? Close collaboration with the final users is really important to target the solution to their actual needs, to get training data for your generator, but also to be in the loop for any update that might break the generator. And this is highly possible when you deal with dynamic and evolving situations like in game production. And again, this shows some potential, but there's still a lot of research that needs to be done, especially if we talk about other genres, like I mentioned at the beginning. But so the whole system has been created in mind to be a tool for level designers to iterate and create, get their creating use flowing. But in the future, this can be used to create levels that are in line with the player's skill, expertise, challenge, desire, whatever you want to give them. And this is also a soft introduction. We think that we can use reinforcement learning during the generator training, online, instead of extracting the gameplay features offline and then using them for generation. So this is all for my presentation today, but if you have more questions, I will be happy to take them now. Or there's a break later, you can come and find me.